So the best way to really learn principle of mathematical induction is just to continue practicing and practicing and practicing, like a lot of things in math. As a refresher, on the right-hand side of the screen, up near the top, I put the 3 steps plus the conclusion that we learned about in the previous video of how to do the principle of mathematical induction when we are proving. We have the base case, the induction hypothesis, and the induction. Notice we are now on to a second example though. This time, we want to prove that the sum of the first n integers, notice our n integers are going to be different, is equal to n times n plus 1 times 2n plus 1 over 6. So this is really saying the sum of the first perfect squares because we are plugging in n squared for n every time. Let's go ahead and start with our base case. So when we prove our base case is true when n equals 1, just a reminder, we're technically plugging in 1 to our a value to figure out what we are testing. So a sub 1 is equal to 1 squared, which is still 1. So we're still plugging in this 1 for n. This is just something important to keep in mind though, because when we're summing together these integers, we're really summing together the perfect squares. So that's going to come into play later in our proof. If I substitute 1 in for all 3 n's in our equation, I'm going to get 1 times 1 plus 1, which is 2, times 2 plus 1, which is 3, divided by 6. That really is just equal to 6 over 6, which is 1. That's awesome because if I sum together the perfect squares, or the first perfect square, I'm going to get 1. Next, we need to write down our induction hypothesis. Our induction hypothesis for this particular example is going to be that we are assuming that the sum of the first k perfect squares is equal to k times k plus 1 times 2k plus 1, all divided by 6. Now, who's ready for some fun? We are on to the actual proof by induction. Ultimately, for induction, we need to prove that the sum of the first k plus 1 perfect squares is now equal to k plus 1 times k plus 2 times 2k plus 3 over 6. Again, I get this by simply plugging in the k plus 1 for all 3 of these k's in our induction hypothesis. If we want to sum together the first k plus 1 perfect squares, we first would need to have the sum of the first k perfect squares, and then add that k plus 1 term, which would be k plus 1 squared, since that's what we're plugging in as the perfect squares. But we know that the sum of the first k perfect squares is really the exact same as k times k plus 1 times 2k plus 1 over 6 from our induction hypothesis assumption. So we can go ahead and substitute that in here for s sub k. Now, all we need to do is combine this expression with k plus 1 squared. Again, we're going to need a common denominator to add. The common denominator is going to be 6, so I'm going to go ahead and write our k plus 1 squared as 6 times k plus 1 squared over 6. At this time, you can again combine these fractions however you wish. However, I see a common factor of k plus 1 in both of our fractions, so I'm going to go ahead and factor by grouping. When I factor by grouping, I get the k plus 1 pulled out in front, but I'm still going to have the k times 2k plus 1 left from the first fraction, and then I'm going to have the 6 times 1 of the k plus 1s from the second fraction. Why don't you go ahead and take a minute to pause the video and simplify what's inside these brackets. You should end up with a quadratic that is factorable. Once you have that, go ahead and factor to get your final simplified answer. If you simplified and factored correctly, you should have gotten k plus 1, k plus 2 times k plus 3 all over 6, which should look really familiar because that's what we were trying to prove. You just finished the induction step of this proof. Don't forget to include your concluding statement. Our concluding statement is that the sum of all perfect squares should be n times n plus 1 times 2n plus 1 divided by 6. Again, that's for all integers that were perfect squares by proof by mathematical induction.